Welcome back. I am absolutely thrilled you're joining me today because we're tackling one of the most foundational and, honestly, most empowering skills in all of mathematics. We are talking about translation. But we aren't translating Spanish to French today. Instead, our goal is to build complete, absolute fluency in translating numbers across three totally different mathematical languages: fractions, decimals, and percentages. Whether you're right in the middle of prepping for a Cambridge O-level exam, or you honestly just want to decode the data thrown at you in your everyday life, mastering this trio, it's literally a superpower.
Okay, let's take a quick look at our roadmap for today. First up, we'll break down the anatomy of a fraction. Second, we'll get into fractions of a quantity and equivalence. Third, we'll map all that onto decimals. Fourth, we'll unlock the power of percentages. And finally, we'll wrap it up with our key takeaways. Let's dive in. All right, Section 1, the anatomy of a fraction. Before we can do any translating, we've got to get our basic numerical vocabulary locked down tight.
At its core, a fraction is really just a number written in the form of a over b, where a and b are integers. To anchor ourselves, let's map out the geography of a fraction. The value on the top, that's the numerator. That tells you exactly how many parts you have. The value on the bottom is the denominator, and that tells you how many equal parts the whole thing is divided into. Just think of it like a giant pizza. The denominator is the total number of slices the pizza was cut into, and the numerator is the number of slices you actually get to eat. Pretty simple, right?
Now, depending on those top and bottom numbers, fractions fall into three core categories. First, we've got a proper fraction. This is where the numerator is smaller than the denominator, like 4 over 5. It represents a value that's less than 1 whole. Then we have an improper fraction. This is when the numerator is actually larger than the denominator, like 7 over 6. This just means you have more than 1 whole. And finally, we have a mixed number, which is exactly what it sounds like. It's a mix of a whole integer and a proper fraction together, like 1 3/4. And here's a golden rule to remember. An improper fraction can always be written as a mixed number and vice versa.
Let's actually put that rule to the test with a specific example straight from the textbook. How exactly do we write the improper fraction 17 over 6 as a mixed number? Take just a second to think about how you'd approach this. Got it? Okay, let's reveal the algorithmic rules.
Here is the logical step-by-step breakdown. Step 1, we just divide the numerator by the denominator. If you have 17 pieces and it takes 6 pieces to make a whole, you divide 17 by 6. That gives you 2 whole parts with a remainder of 5. Now step 2 is where we format our answer. You take that whole number 2 and you literally just place it right next to the remainder 5, which you write over the original denominator 6, giving us 2 and 5/6. Now the textbook gives us a really crucial note here. Did you catch it? The denominator of the mixed number stays exactly the same as the denominator of the improper fraction. It's still a story about sixths.
Moving right along to Section 2, fractions of a quantity and equivalence. Let's see how we can actually apply and manipulate these numbers. Notice how these 3 squares are totally identical in their total size, but they're divided up in completely different ways. The first shows 1 out of 4 parts shaded, so that's 1/4. The second shows 2 out of 8 parts shaded, or 2/8, and the third shows 4 out of 16 parts shaded, so 4/16. But here's the thing, even though the numbers look totally different, the exact same amount of physical space is shaded red across all 3. These are what we call equivalent fractions. They're totally equal in value, they're just wearing different numerical disguises. But notice that 1/4 uses the smallest possible numbers. We call this its simplest form.
And this brings us to an absolutely essential skill, simplification. I want you to figure out the simplest form of the fraction 18 over 24. How do we strip away the disguise and get this fraction down to its fundamental, smallest integer parts?
Well, the absolute most efficient way to simplify fractions in a single step is by finding the highest common factor, or HCF. First, we look at 18 and 24 and ask ourselves, what is the largest number that divides evenly into both of these? Now sure, 2 works and 3 works, but the highest common factor is actually 6. So for step 2, we just divide both the numerator and the denominator by 6. 18 divided by 6 is 3, and 24 divided by 6 is 4. Boom, our simplest form is 3/4. Using the highest common factor gets you straight to the finish line instantly, and it really prevents those tiny, careless errors from creeping in.
All right, Section 3, decimals. Let's map these fractions directly onto our decimal system using division and place value. Here's a cool fact.
Every fraction can be written as a decimal, and every terminating decimal can easily become a fraction if you just understand place value. Let's look at the decimal 0.245. We look at the very final digit, right, which is the 5. That 5 sits in the thousandths column, and this gives us a fantastic shortcut. Because it ends in the thousands, we can write the entire number directly as a single fraction over 1,000, 245 over 1,000. From there, you just simplify. Both of those numbers divide cleanly by 5, reducing it beautifully down to 49 over 200. Place value literally does the translation work for you.
Now, when you convert a fraction to a decimal using division, you're always going to get one of two outcomes. The first is a terminating decimal. This just means the division eventually stops cleanly. For example, 5 divided by 8 is 0.625. It finishes right there at the 5. But then you have recurring decimals. If you divide 1 by 6, you get 0.16666, and that 6 just repeats indefinitely. There's no end to it. Instead of writing 6s forever until our hands cramp, mathematicians use dot notation. You simply place a tiny dot directly over the digit or the sequence of digits that recur. So 1/6 is written as 0.16, with a little dot hovering right above that 6.
But what if we need to go the other way? What if we're given a recurring decimal and we need to translate it back into a clean fraction? This is genuinely one of the coolest algebraic tricks in the entire textbook. Let's look at example 4.5. We want to convert 0.3636 repeating into a fraction. We start by assigning this recurring decimal to a variable. We'll say, let n equal 0.363636.
Now, what is really fascinating here is how we manipulate that equation to trap the repeating part. Because the repeating pattern, the 36, is exactly 2 digits long, we multiply both sides of our equation by 100. This gives us 100n equals 36.3636. Now, stack that directly above our original equation, n equals 0.3636. Notice how the infinite repeating decimals line up absolutely perfectly behind the decimal point?
So, the crucial moment is what happens next. We simply subtract the bottom equation from the top. And when we do that, those infinite repeating parts completely eliminate each other. Poof, gone. 100n minus 1n leaves exactly 99n. And 36.36 repeating minus 0.36 repeating leaves a perfectly clean whole number, 36. We're left with the incredibly simple equation 99n equals 36. Divide both sides by 99, and n equals 36 over 99. Simplify that by dividing by 9, and you get 4/11ths. We literally just captured infinity inside a neat little fraction. How cool is that?
All right, we've made it to section 4, the power of percentages. It is time to talk about the ultimate standardized fraction. To truly understand percentages, you really just need to look at the word itself. Percent literally translates from Latin as out of 100. It's simply a fraction with a permanent, locked-in denominator of 100. So when you hear someone say 75%, it just means 75 out of every 100. It's the fraction 75 over 100. And because dividing by 100 moves the decimal place exactly twice, it's also instantly recognizable as the decimal 0.75. Honestly, percentages are just society's clever way of forcing all fractions onto a level playing field, so they're super easy to compare.
Let's look at the pipeline of converting a normal fraction into a percentage, using example 4.6. Say we have the fraction 3/8. Step 1, we convert it to a decimal by dividing the numerator by the denominator. 3 divided by 8 gives us 0.375. Now step 2, to turn any decimal into a percentage, we simply multiply by 100. 0.375 times 100 shifts that decimal 2 spots to the right, giving us 37.5%. From a fraction to a decimal to a percentage, it's practically a straight line.
Now, while you absolutely can calculate these conversions every single time, the textbook provides this crucial equivalence cheat sheet for a very good reason. These are the most common values you will ever encounter: halves, quarters, tenths, and fifths. Knowing off the top of your head that 1/4 is 0.25 and 25%, or that 1/5 is 0.2 and 20% is going to save you massive amounts of time. Whether you're navigating an intense math exam or you're just out trying to calculate a quick discount at a store, memorizing this specific table is a massive cognitive time saver.
And that brings us to section 5. Key takeaways. Let's lock in all this newfound knowledge.
Here are the absolute fundamental principles you need to retain today. Remember the anatomy. Proper fractions are less than 1, improper fractions are greater than 1 and can become mixed numbers. Fractions of equal value are equivalent, sure,
But a fraction is only in its simplest form when the numerator and denominator share no common factors other than 1. When dividing, remember that all fractions translate into either a terminating decimal that ends cleanly or a recurring decimal that repeats forever, which, as we saw, we can totally capture using algebra. And finally, percentages aren't some mysterious fourth category. They are simply fractions with a denominator of 100. They are all completely interconnected.
And that officially brings us to the end of our explainer. We've successfully demystified the rules of translation. But remember, math isn't just about passing tests or getting good grades, it's the underlying code of the world around us. So I'm going to leave you with this thought. Now that you can fluidly translate between fractions, decimals, and percentages, how will you decode the numerical data hidden in your everyday life? From bank interest rates to election results, you now have the exact tools you need to see what the numbers are really saying. Thanks so much for joining me today. Keep learning, keep analyzing, and I'll catch you in the next one.